today on the third session of this webinar series. So the title of our webinar today is Design, Deploy, and Test Battery Management Systems. Again, I'm Romeo. I'm from TechSource here in Singapore, and I'll be actually guiding you throughout how we can use model-based design and real-time testing to accelerate the development for battery management systems from early modeling all the way to hardware in the loop validation. So we'll try to explore both engineering challenges and solutions offered by MATLAB, Simulink, and Simscape. So before we start, my team will be having an entry poll launched so that we can understand you more better and then understand how you are actually maybe using um, um, Simscape, Simulink, Simscape, MATLAB, and maybe Simscape battery if you are using. So let us please do have the entry poll so that we can actually um, understand your needs for us to be able to deliver something for you today. Hopefully, this one will be a learning item for you uh, in this today. Okay, so I think we have. Um, the entry poll starting already. So yeah, yeah. So there are more of students and researchers. We have here also some software engineers who are in today, and I think there are some managers also who are doing this type of applications and test validation engineers also. So yeah, it's okay. So okay. Yeah, thank you very much for the entry poll. I guess it gives us some understanding or overview of who are we talking to today, and hopefully we are able to actually deliver this webinar to you and more of like help you actually in your daily work with battery systems and hopefully share the knowledge that we have in using MATLAB and Simulink for your modeling and then test and validation and safety certification. So yeah. So let me move forward with our agenda for today. Uh, we'll begin with a quick overview of BMS operations, then move on into building blocks and parameterization of battery pack models. And we'll take a look at how we can design and validate BMS or battery management system algorithms. And then finally, we'll have some discussion on hardware in the loop testing and how it enables actually safe and efficient verification. Um, yeah, so we'll have BMS algorithms and hardware in the loop for this agenda. So hopefully this one will help you to actually develop your battery management systems, modeling your battery models, and then deploying it for your verification testing or integration testing using hardware in the loop. So as you know, battery management systems are also safety critical systems. Long iteration cycles are being done. Collaboration gaps between hardware and software teams is a challenge. And then the challenge of testing of every possible operating conditions actually make it very difficult for teams to actually collaborate together. So this is where actually where model-based design offers what we call maybe a clear advantage for simulations, code generation, and multi-domain modeling. All may shorten iteration cycles and improve your confidence before you actually have physical testing of your battery systems. So hopefully this one can give an overview of how we can have hardware and software teams working together to develop your battery systems and improve shorten cycle times, iteration times, and improve confidence of your systems even before actually you have the physical assets or your testings are being done. So just to give you an overview of how we see the architecture of a typical battery management system, definitely it includes the battery, maybe not only a um, single cell battery, definitely, but it's definitely a battery pack which have series parallel combinations all together so that you can have your capacity requirements and then your voltage requirements. So this is how actually we manage everything from cell diagnostics, for example, balancing SOC or from battery cell balancing, and then SOC estimation or state of charge estimation, and then you're also doing fault detection, and then at the same time you're also checking thermal management systems of your battery management controllers. So these are just an overview of how we are actually developing these systems for the battery management architecture. So there are two levels of simulation that we like to introduce to you. One is on the plant modeling, which is the battery pack, and the other one is actually for the development of the control systems, which is the battery management systems. So how do we start, or where do we start? I guess that's the question. So with this slide, actually, I just want to show you that, of course, definitely the foundation of this understanding is based on the cell behavior of this system. So we need to gain insight of how we can actually develop a model for the battery cell and how we can model it using our tools. So an example of this is by modeling the cell dynamics accurately, so we can actually gain the insight into the performance of the battery. And for example, also degradation of the battery or aging or fading, in other words, or how do we include fault analysis in our systems? So this is just an example of an equivalent circuit that we have for a battery. So this is just a simple one. There's an equivalent circuit common to existing literatures right now. So we have a voltage source, which accounts for the open circuit voltage of the battery. Then we have the resistor, a terminal resistance. Um, we have the RC branches, which accounts for the time constants, frequency response of the battery. And for some chemistry, there are also charging losses or self-discharge are significant. So, but in this case, for lithium chemistries, they are often ignored or maybe just minimal effect in this case. So finally, we have this circuit which is a function of state of charge, temperature, sometimes current and voltage. So this relationship may be highly nonlinear. So this is the equivalent circuit that we have for this cell. So using our Simulink and Simscape battery models, we can actually typically begin with an equivalent circuit model, capturing all of these parameters that I've shown you, open circuit voltage, terminal resistance, transient dynamics, which are the RC effects, and the parasitic effects. So these are shown here in this table. So for example, state of charge, and then temperature variation, no load voltage, which is the open load voltage, terminal resistance. So these are just some simple you know, main characteristics of the battery. But with Simscape and Simscape battery, we are not limited to those basic parameters, but there's also some charge dynamics that we have, for example, or maybe you have data for fading or fading aging effect for the batteries. So these are the ones actually you can also use for the battery cell blocks that can be used for your um, parameter modeling of your cell batteries. So to just give you an overview of Simscape, Simulink, Simscape, and Simscape battery. So we have battery cell blocks that can be parameterized as a function of, let's say, SOC or temperature. So Simscape battery provides design tools for modeling and simulating battery and battery energy storage systems. So in this case, you can use these tools to test battery architectures, design battery management systems, which are the control of the system, evaluate battery system behavior across, let's say, normal applications or functional testing. But you can actually also do extreme conditions, maybe temperature-wise or fault conditions. You can actually put place within the battery itself, which you can do actually virtually. So you just imagine you can do this one virtually rather than the actual physical asset, putting in faults. So you can model these systems by assembling these components in a schematic, like for example, this that I'm showing, which shows a battery. Actually, this is the battery. And then we have a switch, which is a relay. And then we have a simple battery management system, and then a CCCV charging system. So actually, all of these are internal to Simscape and the libraries which are used in Simscape battery. So these design tools help you to automate creation of battery packs. So in this case, you can create not only one cell, definitely. When you're designing a battery pack, you need a lot of uh, cells in parallel and then in series. And maybe this one can have more modules in this case. So Simscape battery helps you to actually modularize your batteries, and then in the end you will actually connect all of these modular battery systems into a battery pack. So in this case, for example, you can see this. So actually this battery has different modules in a sense, which are parallel and series to each other to meet your battery requirements in the design. So in an overview, Simscape battery helps you to actually develop all these systems in just one environment. In this case, a Simscape, I mean Simulink environment, where you have the plant model for the battery itself, and then you have the control systems that are there inside the same environment. So in one simulation tool, you are able to actually develop all the requirements that you need for your battery management systems. So yeah, so for the key features of Simscape battery is uh, Simscape battery actually helps you to assemble cells into packs. In this case, modeling thermal behavior also, and then simulating algorithms like charge, discharge, and protection systems. So it automates this process by letting you adjust the trade-offs between, for example, let's say fidelity and simulation speeds. So in the schematic that you saw earlier, so you can see here there's a control system that is there, and then you have the plant model, which is actually this mechanical and electrical system, and then you can actually do an implementation for this. So this can be done with implementation with the software using maybe a microcontroller or a Hill system, in this case, hardware in the loop example. So this one can be done through this Simscape battery application. So let's get started with the battery cell. So we have a critical step actually when we're doing this cell modeling. In this case, the model should match real data as close as possible, right? So we have certain models that we have. And then, for example, in this case, we also have experiment data. And then from here, we have an output, and then we compare this data and then see if we have a similar simulation in this case. So this is our objective. Usually when we have data plugging in data or parameters to the battery cell in our simulation, we usually use our data sheets, for example. But most of them doesn't actually behave like actual or experimental values or data from our testing, actual battery testing. So what we can do there is actually do a parameter testing for this system. So for example, we have an input current, input voltage, and then we output a voltage and see the comparison between our model and the experimental model, experimental data. So we are comparing these two and then see if it's very close to each other. So the objective there is if it's not, then we can do a parameter estimation model so that we can actually check if there are differences between our simulation. So in this case, for example, we have a data. So the blue data here that you see here is actually the actual data of the battery. This is almost similar like an HPPC data, but much more on the discharge voltage in this case. So this blue line is actually the actual simulated, actual battery cell measurement. The yellow one is actually the parameters that we use actually for the model of the cell only within the Simulink or maybe the tool. So in this case, you can see that it doesn't match the actual behavior of the system. So after doing parameter estimation, um, you can see that it's almost similar response now. So it adjusts the parameters of the cell until it meets almost the same responses of the system or the cell in this case, in the battery cell. So how do we do this? So it's like by fitting the model outputs to the measured data, we are actually creating like we can say a digital twin of your battery cell. So it acts like a real cell in its normal environment. So repeating this across temperatures, we build lookup tables, for example, to capture the behavior with under realistic conditions. So you can actually do a parameter estimation for this application. Then after that, how do we do this parameter or battery cell parameter estimation? So I have this. So what we do usually is, so this is the discharge data that we have. So this is the current discharge for this cell. And then the red line here is actually the actual measurement, experimental measurement of the battery cell. And then the blue one is actually the model response. So in this case, we will need to do a battery estimation run to check these systems. So we have this pulse data, which is the actual data from the experiment. And then we have this battery cell parameters too for MATLAB and Simulink to actually adjust later on and see if this one can be changed and then meet the required actual response. So in this case, I have run, in this case, a progress report. You can see that internally, MATLAB is actually changing these parameters here and then checking out how the responses will be. So later on, you can see that actually it is the orange or yellow line actually or red line is actually changing. So you can see here that there are changes now with the parameters that we have here. With the changes here, you can see that the data, or I mean the responses of the model is actually changing. It's actually converging to the measured value. So this makes it very good so that the parameters are almost similar to the actual responses of your battery in this case. So this helps you to actually put or give, make your models much really closer to your actual applications. Yeah, so in this case. So let me move forward on the how we can start actually doing simulations in this case. So now we have done cell dynamics, right? So we have changed the parameters. So now we are, let's say we are confident that we have developed the cell model near our actual responses. Then we add thermal and aging and fault dynamics in this case. Then we evaluate certain series, parallel counts, or cell configuration. In this one is to meet your capacity and efficiency requirements. And you design your battery pack itself in this case. And then you evaluate system level behavior. For example, you have a battery and then you will connect it to, let's say, a motor or an inverter or a charger or any vehicle. For example, in this case, maybe vehicle dynamics, or if you're using it with microgrid application, maybe you can have those load applications that you have, and then check the battery system's behavior for your case. So once the battery model is in place, so now we can actually develop or design the algorithms for SOC estimation, for example, balancing and fault detection, for example, and then thermal management of the systems. So this allows us to evaluate algorithm performance under, for example, let's say we have a charging state or a discharge state or a transient conditions. So you can see here there are a lot of battery management tools that we can use. For example, in this example that we are showing, there are like fault detection, for example, charge management, for example. You have also a state machine where you can actually, this one is the one driving for your state of the BMS. In this case, for example, you are in a standby state or in a charging state or a discharging state where maybe you are driving, or this one is implemented in the grid, for example. So you also have a state of charge estimation where you have these systems to actually allow, for example, Coulomb counting or extended Kalman filter applications, which can be validated here in this software and then deploy it in the hardware later on. So how developing BMS algorithms along with the plant model. So this one gives you an overall application of the system. So you validate, for example, state of charge in this case, or state of health, balancing, cell balancing, maybe some kind of current or power limit, thermal management, and diagnostic algorithms. So these are the ones that you usually do for the evaluation of the testing. So this is an example of an evaluation using a state of charge estimation using Coulomb counting or unscented Kalman filter or extended Kalman filter in this case. So there's a comparison in this case. So it depends on what algorithm that you want to use for your applications. So the motivation here is to actually, develop it in just one system, in just one level of IDE, in this case, Simulink applications. Then later on, the next step after you have done your system, battery system plant, in this case, the battery pack, you have designed your battery management systems, let's say those control systems, um, all those state of charge measurement, for example, cell balancing has been developed. The next step is actually for you to actually generate embedded code from your validated models. In this case, Simulink allows us to move directly from algorithm models. These are from Simulink models. And then you move on to C++ code. So this one we generate, Simulink is able to actually help you out to generate this code. So this is why we are actually doing the testing, verification and validation. This is why it is very important, especially since errors originate actually earlier in the development, and the problem is we are actually discovering uh, errors later in the in development, which we should have seen earlier in the design. So Simscape Simulink is able to actually help you out. In this case, early testing for your battery management systems, verification and validation of your systems. So you can see here there's a generated code for this state machine, and in this case, this one is generated from your Simulink models. In this case, you are able to actually generate from Simulink models to the code generation example. So in this case, this one. So you Simulink is able to actually generate C++ codes for your Simulink models for your, in this case, battery management systems to be developed in Simulink, and then generate the code and then later on implement into your hardware embedded systems in this case. So normally or usually, this question come up. So did we generate our code early? Is this ready to ship? Or what are the bugs that we are experiencing? What are they and how do we find them? So actually, let's find out how we can actually help in this applications. Why we are doing testing? Why are we doing verification? And why are we doing validations? There are two things that I come up in my mind. So number one is because it's safety critical systems. So we need testing and verification of these systems, these battery management systems. Number two is we want to meet compliance. So if you are working on functional safety, for example, or safety critical systems, this part is actually requires us to do the testing, verification, and validation, and of course, to make us more confident on the algorithms that we have done earlier on, right? So in this case, we will do all the testings required for this development. So how do we help in this endeavor? Uh, let's see a typical development workflow. So in this case, you will see that most of the errors are introduced actually at the start of the applications. So most of it are maybe coming from requirements or specifications. So some errors are already there within in your workflow. Then later on, because of your testing, you find a few of those errors, and then later on, you find other integration errors, or maybe in the field, which is not really good, right? You don't want to find errors in the field. Actually, you still want to find the errors within your development cycle. So this is the challenge actually that we want to share with you, because errors are actually introduced earlier in the design phase, but the problem is they are found later in the development. Hopefully not in the production phase, but uh, usually this is what happens when we are not fully doing some of the testings that is required for our evaluations. So how do we validate design via desktop simulation? So that's what we do with Simulink and Simscape. So this is how we are actually evaluating these systems in this case, to actually correlate our system requirements. And then from those system requirements, we actually develop the system model. So from here, we are developing it from the requirements. But how do we actually interconnect all these systems? How do we design from requirements and then design it to your models and do the testing to find the errors that we have? So how do we actually interlink all of this in this case? So I like to introduce you with the model-based design workflow. So this is the workflow that we have for a model-based design environment, where we have the requirements, which is usually where we start our design, right? So we have a customer or we have an internal requirement for our systems, right? So it starts with the requirements. And then from there, we design our models. That's where we design our plant models, or in this case, maybe a battery or a battery management system. So we design all those control systems in this case. Then from there on, we model, from the models, we generate codes so that we can do our testing, compare that generated code to our models, and then check it actually with the hardware implementation in this case. So this is the usual model-based design workflow. So in contextual requirements, there's model verification to discover design errors. So with model-based design, it happens continuously. So even at the start of your design, you're already doing the testing and performing back-to-back testing. You're doing tools where you're working with tools like Simulink test, coverage, Simulink coverage, and design verify. Later on, I will have a short demo to show what are the tools that we are using for this workflow, and then how you can actually, for example, do a test harness to isolate the components for validation while doing coverage metrics, for example, or formal methods of detecting untested or unreachable logics. So this results in faster development. So testing faster also, there's fewer surprises late in the process. So we are more confident with the code that we have generated and eventually runs in your hardware. So yeah. So code verification, these are just, back-to-back simulations and verification so that the whole system, in this case, we are able to actually test your models. In this case, generate the code, compare your codes with actual hardware implementation, and see the algorithms working in hardware. So in this case, faster development, reduce cost, lesser hassle for us, and this one is actually more of the engineering in this case. So the engineers are able to actually um, um, focus on the development rather than, for example, coding, rather than all these manual steps. We are able to actually do some automation for your testing. So these are just common questions on when we're doing the designs. So previously, when I was doing also my designs, these are the first questions that comes up. Does my design meet the requirements? So is it functioning correctly? Uh, how do I test it or completely test it? Is there a bug on the hardware, or is it the software? So these are just some questions that comes up during our development of our systems. So in this case, we are able to actually help you to actually link up from requirements. In this case, you are able to link up your requirements to your models. So these are just an example of managing requirements into your models using requirements tool editor or requirements toolbox. So we are actually importing requirements from your maybe a Word document or an Excel file or a standard interface requirements file. For you, actually, we can actually interface with those systems, like for example, IBM doors, which have this RecIF requirements interface files. So yeah, you can author and refine requirements within actually Simulink and in this case Simulink without having another software in this case. So yeah, so requirements toolbox help us to work with importing or authoring requirements, modeling requirements actually, and then traceability reports, coverage and impact analysis, which are defined for your applications. With this, once you have developed your requirements and then develop your models, what next is to actually do testing. So we develop and manage and execute testing using Simulink toolbox to develop. If you have a lot of testing, this test manager is able to actually help you to manage all this testing from simulation and then equivalence testing, or if you have baseline testing, this one baseline is comparing your results to an original baseline testing. And if it meets with your requirements, Simulink test generates a report for these applications. So it helps you also to generate test harnesses and test. You are able to actually develop test for your applications. So next is much more of Simulink coverage. So this measures the test coverage of your models and the generated code. So the models are being tested and also the generated code. So these are full testing of from the model itself until also the generated code. In this case, it also have this reporting for your references. So addressing some missing coverage. So we know from many customers that you define test, right? And then measure the coverage. It is difficult to actually challenge to reach 100% of the coverage. So it is frequently the last few percentage that are most of the efforts actually in this case. So yeah, so with Simulink Design Verifier, you are actually able to have a test generator. So in this case, helps you to develop the additional testing to complete actually your coverage in this case. So, and when combined with your initial testing and with this suite actually achieves a complete coverage. While you can do this, you are actually working to simplify or automate your releases in this case. So test generation is to identify, for example, dead logics. When the test generation procedures gives you coverage of how much is uh, taken into consideration for your testing. This one is much more of design error detection. So with Simulink Design Verifier, uses formal verification, design error detection for your models, and generate test vectors for proving formally your to if you're meeting your requirements. So beyond that, actually, we must test algorithms not only in the models that we have, but we want to test these algorithms on real hardware. So in this case, we are directly checking battery testing. But of course, battery testing in the actual physical one is actually costly. It may be also slow and maybe unsafe if, for example, you're doing some testing for fault scenarios. So instead, we may use battery emulation, which is developed with hardware in the loop systems or real-time systems. So this is an application that you can actually see if you have some kind of real-time systems where you run hardware in the loop. So models are running actually in real time systems and then simulate cell voltages, pack current, and then let's say thermal behavior. And then faults can be actually injected safely. So this one is actually also automating our testing, thus reducing our time dramatically for our testing. So these are just some examples, of how we can actually, because it's difficult to actually do testing with actual battery systems. So usually, especially for fault diagnostics, so we usually use this real-time systems to develop our implementation for this system. So one example is of a real-time system is the SpeedGoat hardware, where you can perform platform to execute large-scale battery pack models, for example, let's say with high-frequency dynamics, for example, sensor emulation and fault insertion. So this bridges the gap between desktop simulation and your real-time integration for validation. So in this case, you are able to actually execute these models in real time to emulate cell dynamic for the batteries using, in this case, for example, a speed goat real-time system. Yeah. So you have cell monitoring, and then the plant model you can run within the battery emulation, and then you have your own battery management controller unit in this case. So yeah, testing reduces time, help us to develop test faults conditions safely without actually doing the test faults in the actual battery itself. This makes it safer to do the testing, and we can do automated testings for these applications. So yeah, so just to continue, we are able to actually help on this challenging in the challenges in actually executing real-time applications with this sensor emulation using real-time systems. So you're able to actually easy for Simulink in this case. We have Simulink real-time, which is actually directly converting your models into real-time systems with the SpeedGoat application. So this is actually easier for us to develop by reducing model complexity, in this case, helping you to prepare your model for real-time simulation. So this is what I was talking about earlier. So you have Simulink real-time for rapid prototyping and hardware in the loop testing in this case. We have this hardware developed for this application, like the speed goat in this case. So we have a Simulink, for example, the basic applications for this, and then signal monitoring and instrumentation. And then we have also deterministic real time, definitely, because it's running in the actual systems. So before I close this the webinar, I would like to share a little bit on the actual application. So of a model, for example, with BMS or battery management system. So actually, this is the one I'm showing in my screen is actually the actual battery management system algorithms that we have. So earlier on, we are talking about the plant model, which is the battery, and then the algorithms for controlling this battery system. In this case, for example, SOC, measurement, control systems for your charging and discharging, for example. So these are all actually developed in a single environment. So let's see how it looks like inside the battery pack, for example. So we have a thermal port also. So for this case, where it is actually connected to this temperature source. So this one is the ambient temperature of the battery, and then it's connected through this conductive heat transfer for the battery cell. So this is what we call multi-dimension simulation, where you're not only simulating electrical systems, but in this case, also thermal systems. In other applications, these thermal systems is actually also connected to certain fluid, how to say, dimensions, where you are actually working with, for example, to reduce the heat of your systems, you are actually having certain fluids that are added to your system to lower your temperature applications. So these are just some of the applications that you can do with Simscape and Simulink in this case. So if we go inside, so we can show that this is the battery pack cell that has been designed for this application. So you can see there are a lot of modules for this model. And then from these modules, you're actually implementing these systems internally as a one pack system for your battery system. So that is the plant model that we have for the battery system. So once you have done the plant modeling for your battery, so you start to develop your software or your control systems in this case. So there's a lot of applications here that I can show. For example, current or power limits in this case, uh, contactor management. These are more of a relay control or systems, and then fault detection for your battery systems. You have a state machine. This state machine is actually a state control where you can actually see what is the state of the battery system, the battery management system. Because this example is on the automotive side, so it has a driving state where when the battery is engaged in loading the motor, in this case for the vehicle, electric vehicle. Then there's a state also where it's in standby, or it's in charging mode, or if it's in fault mode in this case. So these are just some examples of the system that we have within this battery management system. So there's also an SOC, or state of charge estimation system. So this uses actually the Coulomb counting. So this one actually uses the libraries that we have in Simscape library to develop this SOC estimation using Coulomb counting in this case. So there's also cell balancing logics that is designed for these applications. So this one is also a library that is used that we have for Simscape battery for the development of this kind of applications. So this is the whole system overview of the testing of your battery in this case. So let me show you how our this software is actually interlinked with the requirements. So let me show you the interlinking. So there's a perspective, for example, the requirements. So if you see here, there's requirements editor, and then this actually requirements are actually from your, maybe coming from a Word document, or it can be an other systems document, or you can actually use itself the requirements toolbox itself within MATLAB or Simulink. Then you can actually link your systems. In this case, for example, these green lines shows that these requirements are actually implemented within the systems in this case. I haven't done a test, that's why it's not yet verified here, but in this case, you can actually already see where you have implemented your requirements for this testing. So this is just one example of how we can actually relate the requirements and then your model. So you can have a linking within your system itself. And then after that, you are able to actually do a testing also. So earlier on, I told you about the harness, or the test harness, and Simulink Test Manager. So Simulink Test Manager enables us to actually create multiple test series of tests in this case. So this is just an example. So there are, I think, 6 tests for this. For example, the state machine that we have seen earlier. So these are just automation. So you can specify all the test conditions within this test manager, and you are able to actually run all of these tests at one go. So these are just example of some automations for your testing for your systems. Other than that, for example, if you are developing your systems with let's say, for example, you have compliance for your systems. So we talked about compliance earlier. So Simulink have this model advisor, so which checks your compliance for your application, or for this development. In this case, for example, if you are working with ISO 26262, for example, if you are in the automotive industry, maybe you are using 26262 as a compliance requirement. So you can actually check the model if it meets ISO 262 compliance system. So it can create a report for you using Model Advisor. So those are just the tools that we have in this case for developing battery management systems for your applications. Yeah, so in summary, we have shown you how we are developing safety critical systems, in this case, battery management systems with long iteration cycles, collaboration gaps, between hardware and software teams is usually the requirements. So in this case, we have shown you how the requirements is actually meeting or are being embedded within the models itself, and then actually executing these requirements for your applications. So, and then at the end, we are doing the challenge of testing, right? So it improves actually our testing because we can do some automations for the testings, and some of it actually to develop the coverage, right? So we are able to actually use the tool to actually generate the remaining test for testing to complete our coverage. So this is where the model-based design offers a clear advantage. So simulations, code generation, and in this case, multi-domain modeling, which is not limited to electrical system simulations, but also thermal management, and yeah, and any other domain. In this case, for example, I said earlier, like fluids. This improves our confidence even before the physical testing occurs, actually. So in this case, we are able to develop a virtual testing, in this case, for our applications. So just to conclude our discussion today, we have shown you how model-based design transforms battery management system development for your battery systems. So we started with modeling the cell and battery pack behavior, for example, and then we design and validate these algorithms in simulation and generate production ready code. And then finally close the loop with hardware in the loop testing and in this case, verification. So we gain more confidence in our design and works towards more of, in this case, of this example, more of a safety certification or compliance. So this approach reduces iteration cycles, ensures traceability for your safety certification. So this is from the requirements to your application and then to your deployment, and then gives you confidence that your BMS will perform reliably in the real world. So yeah, with that, thank you for your attention, and yeah, we can now open our the floor for the further questions. And this is not the end of the electrification webinar. So actually, there will be two more webinar series for this um, seminar series. So there are two more, more of like for motors, and then another one for AI applications for electrification. So hopefully you can attend those webinars later on your time. Okay.